So thanks, everyone. Again, looking at a climate change resiliency study that we did in Anne Arundel County, Maryland. It's an outline for the presentation. I'm going to cover the study scope and the project objectives. We're going to look at how we modeled inundation for this study, look at the methodology we used and some of the results. I'm going to circle back to looking at some of the adaptation measures, so not just what assets are at risk, but how do you go about fixing those vulnerabilities. And then I'll circle back for questions at the end. So looking at the study scope, again, Anne Arundel County, Maryland, it sits on the western shore of the Chesapeake Bay. A significant amount of its border is coastline, so they're particularly vulnerable to things like sea level rise and storm surge. Their Department of Public Works received the FEMA BRIC grant that allowed them to assess roads and bridges for 3 different climate stressors, so storm surge, sea level rise, as well as precipitation change. Ultimately, we evaluated over 1,800 miles of county roadways, as well as 86 of their major NBIS bridges. So the objectives of the studies, we were really building on a few prior studies that were conducted in a similar vein. So the Maryland State Highway Administration in 2014 and 2019 conducted a vulnerability assessment of their roadways. The 2019 one also included bridges. And in those studies, they had a lot more robust data sets available for their state roadways. The 2023 Anne Arundel study that looked at sea level rise only, and it looked mainly at structures and other properties that were affected by sea level rise. So the challenge with this study with the county was to be able to evaluate their local roads in a consistent methodology with the data that they had available to them. And then we were going to summarize the results and present it to the public. So looking at how we handled inundation modeling, one of the ways we pivoted with this study compared to the prior studies, all the prior studies looked at a horizon year, whether it was 2050, 2065, 2100, and then picked, based on climate science at the time, a certain sea level rise elevation, and then they modeled that for impacts to these assets. In this case, with this study, we went to the NOAA's sea level rise data that has increments of 1 foot all the way up to 10 feet, and we ended up modeling all 10 scenarios. And this will give the county maximum flexibility to see what assets are at risk at different levels of inundation. So as climate science evolves, they can pick the modeling scenario that's most relevant to current science. We ended up picking 1, 2, and 3 feet is increments for permanent inundation for sea level rise, and everything 4 foot and above we considered storm surge. So looking at our analysis methodology, again, we're looking at just roads and bridges with this analysis. We evaluated each of those asset types against sea level rise, storm surge, as well as precipitation change. And then one of the other ways that we pivoted this study, a lot of times you see these risk analyses and you come up with some sort of composite individual number score. We decided to pivot to a 2D risk matrix style where we quantify the likelihood of impact on a given asset, and then the impact itself of that asset. So if you were to remove a road or a bridge from your transportation network, how much of an effect does that have on your overall system? And the advantage of this approach compared to composite scores, sometimes you lose the level of detail in a total overall composite score, whereas if you can quantify likelihood and impact individually, you can kind of really drill in and see, okay, am I looking at situations where an asset is frequently impacted or frequently inundated, but maybe it has a low impact on the overall system? You might address that one way. And then you might have another asset that might be at a really low risk for inundation, but if it were to be inundated and taken out, you have a really large impact on your system, so maybe that problem gets addressed a slightly different way. So as part of our methodology for likelihood of inundation, we took each asset and quantified everything in terms of high, medium, and low risk. Looking here at sea level rise, we quantified anything that would inundate at 1 foot as a high risk, 2 feet medium risk, and so on and so forth. Anything that didn't inundate above 3 feet, we just said had no risk at all of inundation. For storm surge, we had the Naval Academy sea gauge data dating back to the 1930s, so nearly 100 years of data. And they have this handy graph on their website that basically outlines the probability of a certain storm surge related sea level rise occurring in any given year. And that translates to a table that looks like this. So on the left you have all the different 1 foot increments of sea level rise, their percent chance to occur in any given year. And then we kind of bucketed those into those same high, medium, and low buckets. For precipitation, this one, the county luckily had a bunch of data for confirmed flood locations, so a mix of like road closures, bridge closures, citizens calling in to report flooding in an area, things like that. We compiled all of that data and created a known flooding areas layer that we were able to then assign a high risk, since we know flooding's occurred there in the past. Then medium risk, just anything within the FEMA 100-year, low risk, anything within the 500-year, and everything outside of that had no risk at all. We did exclude bridges, so if we were evaluating road segments block to block, anything where a bridge crossing occurred, we kind of cut that out of the road evaluation and evaluated bridges separately. For those bridges, we still did look at inundation layer, like we just talked about for the other layers, so looking at sea level rise, FEMA floodplains, known flooding locations. But we also incorporated what we called a sensitivity component. So with the NBIS bridges, as part of that standard data structure, there's a condition assessment associated with each bridge, the height above the waterway as well as the age of the structure. So here we thought it was important to know, even if an asset wasn't overtopping, even the water just hitting the substructure could deteriorate the condition of the bridge over time, and that would also make it more vulnerable to these climate stressors. Looking at how we evaluated impact for all these assets, this is something that we did in a vacuum, so it didn't really depend on the climate stressor itself. There's just one score for each asset. And again, this is just assuming if we were to take this asset out of the transportation network, how will the network as a whole be impacted? This is another place where we had to significantly differentiate from the prior studies. In the Maryland State Highway studies, they did have average annual daily traffic for all of the roadways, and the county, for all their local roads, they just don't have traffic studies or traffic data for all their local roads. The county also doesn't really have evacuation routes. It's more of a state level thing. So we had to exclude things like that. And we came up with two new metrics that the county could use to evaluate their entire road network consistently across the whole data set. One was evaluating how long a drive would be detoured if that road were to be closed, and we called that detour 1. And another attempted to estimate the amount of flow or the amount of traffic through that roadway without having a traffic study, and we called that detour 2. So looking at detour 1 in a little more detail, we just used Esri's network analyst to go in and create start and end points at the end of each road segment individually. And then we put a barrier on the segment itself and tried to draw a route. So that route would then see if you can get from one side of the road to the other, if that road were to be knocked out. And then we quantified the level of detour based on the differential between the detoured route and the length of the route itself. So if you have a short detour like we're showing here, like a quarter mile or 1/10 of a mile, it's really not a big impact on your system, no big deal. But if you knock out a bridge and you all of a sudden have a 5-10 mile detour, that's a much bigger impact on the system. Some routes won't be able to be detoured at all, so the county, as we'll see in an example here shortly, has a lot of what they call one-way in, one-way out roads. So if a certain road gets knocked out, an entire community is now cut off from leaving the neighborhood at all. Looking at detour 2, this one we're trying to quantify the amount of traffic that would flow through any given road segment. So we start this as kind of an iterative, cumulative process where we kind of sum all of the homes on any given segment, and as they flow through the system, how we quantify that. So if we look here, all of the colored dots represent the centroid of a given road segment, and the blue numbers represent the amount of homes associated with that segment itself. So you can see here at the top right, there's 3 homes with that green dot. We then create a detour route that goes from that segment all the way to the nearest state route. And we say that that road segment, if people were to leave here, would have 3 homes associated with it. Then the yellow dot, the next one in the chain, there's only 2 homes associated there. So with that red 5, you get the 3 from the previous block plus the 2 from this block, now you have 5. So on and so forth all the way down the system. So by the time you get to that Frederick Road that's closest to the state route, now you have 16 homes that would need to drive through that segment to get to that state route if there was some sort of flooding event in this neighborhood. Now this is just a simple schematic example to look at how the numbers were calculated. This is more of a real world example. So this shows one of those one way in, one way out roads. You have this kind of peninsula there. There's one road that kind of connects to that peninsula. Then you have this neighborhood with a bunch of homes on it. So it ends up being 188 different address points on that peninsula. And if that red highlighted road on the right were to be knocked out due to inundation, all of those homes would then be cut off. So this would get a much higher score in terms of impact to the overall network versus all those roads kind of at the edge of the network that, yeah, they might also be inundated, but they're just neighborhood roads. There might be detours around those roads from other adjacent neighborhood roads that might be a little more higher off the sea level, so they don't get impacted by the flooding. So just circling back again, these are kind of the high, medium, and low buckets we use for likelihood. For the impact, we multiplied the detour 1 times the detour 2. So travel costs, we're calling that, that's the detour length itself. How much further do people have to travel if an asset is impacted versus the volume of traffic if that asset is impacted. And then we really just divided it into percentiles. So the top third, the medium third, and the bottom third gets high, medium, and low. So how does that translate to results? Here we're looking at assets that are vulnerable to sea level rise. As expected, everything's near the coast. And as a result, there's high, medium, and low in terms of likelihood of inundation, as you see in that left column. But there aren't a lot of high or medium impact roads, so, which makes sense, right? You're at the coast, you probably don't have a ton of traffic going through those areas. They get knocked out, less of an impact. Whereas if we look at the storm surge results, you kind of get the opposite. So this is looking at 4 all the way up to potentially 10 feet of inundation, which that inundation will come much further inland, many more roads impacted that have a high impact on the system. So you can see here we have some of those high likelihood, low impact. County might evaluate those one way. Then we have nearly a mile of ones that are low likelihood but really high impact should they get inundated. And then we looked at the precipitation results. Again, this will have a little bit more inland relevance, not just coastal relevance. We had those known flooding locations, whether it was nuisance flooding or road closures or whatnot, as well as proximity to the FEMA floodplain. So again, these are scattered all over. And we're looking at these results individually for each climate stressor, but some of these assets were affected by multiple climate stressors. So again, those might be evaluated differently compared to just the individual climate stressor. So once the county had the results, the next step of the process was to look at adaptation measures. So these are, okay, now we know what assets are affected. Now we know how to sort of prioritize them based on high, medium, and low risk. How do we go about fixing these problems? So to do that, we came up with a suite of options to address specific vulnerability for each asset type. They were organized by the type of asset, by the stressor, so climate change, storm surge, or precipitation, and then the specific vulnerability. Unfortunately, this wasn't just a desktop exercise. It does require some sort of field investigations to identify whether certain vulnerabilities exist. And one of the key ideas with this was to provide both engineering and operation and maintenance solutions to the problem. So an engineering solution might be more permanent and cost more, whereas an operation and maintenance solution might be something that they can implement quickly to solve an immediate problem. So looking at the matrix, I know this is kind of blurry. I don't know what's going on with the projector. I'm not going to read it anyway. But you can see on the left, kind of color-coded, it represents which climate stressor is affected, each vulnerability type. Then there's a list of all of the vulnerabilities. I'll come back to a more zoomed-in view in a couple slides. But then you can see to the right, we have the engineering versus the operation and maintenance solutions. And we have a similar one for bridges. This one's a little more detailed. There's a lot more to inspect and evaluate on a bridge structure versus just a roadway segment. So the county envisions this analysis of these adaptation options as a 3-step process. The county's towards the end of step 2 right now, and we're thinking forward on step 3. Step 1 is to do the desktop and field investigations to evaluate the assets that are at risk. Step 2 is then, okay, now that we know what's wrong with these assets that we've identified as high risk, how do we come up with some sort of concept or design that addresses all of the problems we've identified? And then step 3 is, now that we have the universe of concepts to solve this problem, how do we evaluate where we're going to spend our money to solve those problems? So to kind of start with, they did a case study on a particular road. This is Deal Beach Road. You can see here it highlighted. It's one of those one-way in, one-way out that feeds a community to where if this was knocked out, all these homes would be cut off from the rest of the transportation network. It does sit in a FEMA 100-year floodplain. Modeling does show it would inundate at 2 feet, so whether it's storm surge, which is more of a temporary impact, versus sea level rise, which is a permanent impact, this is definitely a roadway asset that's vulnerable to those things. So looking at the matrix and how they would use it, it's more of like a worksheet, workflow, decision diagram. For each vulnerability that's listed, they have a decision tree. So here, this first one that's highlighted is, do the approaches or embankments show undermining or washout? There's some questions that someone in the field would need to ask and verify to see if that's a condition, and then it even highlights what inspection elements of that asset they should be looking at to make that determination. And then they could decide in terms of the decision-making, is that an issue now? Are you already seeing these conditions in the field? Is it a future condition? Do you see like preliminary signs, or is there no issue with that specific vulnerability at all? And then they would kind of go through that worksheet and arrive at this. So this is, after completing that case study, that vulnerability 2, 4, and 7 were identified as either current or future issues. So now they have a list of the specific vulnerabilities that are affecting that asset, and then how they can then either apply engineering adaptations or some sort of operation and maintenance solution to address those needs. So from there, they would probably come up with some sort of concept, reach out to an engineer. It's outside the scope of our study, and then hopefully come up with some sort of cost, which would then feed into prioritizing which adaptation measures or which solutions for their capital dollars are actually implemented. So the county's still in the preliminary steps of this, don't have any answers. They have a lot of questions that they're trying to consider. So how do they objectively compare viable options across the whole suite of assets that are at risk? How do they compare the selected option or the concept that they come up with based on the vulnerabilities that they investigate in the field? How do they prioritize the investment of their money once they've done all that field investigation and prioritization? So they don't have a simple answer. They're still considering a variety of solutions. They're looking at things like frequency of inundation, or the duration of the impact, whether it's a permanent impact, as with sea level rise, that might require different solutions than more temporary impacts from storm surge and precipitation change. They're also working with their operations, their maintenance folks, as well as their structures and bridge folks to see if there's any planned work on these structures upcoming. Maybe they can add additional capital dollars to include some resiliency components as opposed to just basic resurfacing or whatever other maintenance work they have going on a stretch of roadway. And also, because we have all those detour 2 things calculated, we can sort of estimate the number of homes or the miles of detour we would reduce, so the reduction to the impact on the overall transportation system, that could be another thing. And they're also considering other EJ factors like low income or minority populations, vulnerable communities in their county. And with that, I'll turn it over for questions. Yes.
Were you only evaluating state-maintained roads, or did you also include non-state maintained roads?
So yeah, the exact opposite. So we were only doing non-state maintained roads. It was all the local roads.
More of a comment than a question. I noticed you're using NOAA sea level rise layers in this. We just did a soft rollout last week of half-foot increments.
Oh,
Be helpful for your work.
yeah, that's great. We could run 20, 20 scenarios now. That's good to know.
I have a question on, when you were saying like 1 foot, 2 foot, like what were you basing those numbers off of?
Yeah, so most climate science, if you look at here, I'll go back to that slide. Where is it? There it is. Yeah, so most of the studies we were basing this off of, they picked, like I said, the horizon year. And the county, we went back and forth on this a lot at the preliminary stages. The county thought about, did they want to have a planning horizon of, we want to look through 2030, 2050, what do we want to do? Do we want to just use the same years that these prior studies used? And because they couldn't make that determination, they said, let's just model all 10 scenarios. And then eventually they decided, based on their planning horizon, I think here you could see the 2065 study was about 3 feet of inundation in 2065. So we just looked at 1, 2, and 3 feet, and we just bucketed as low, medium, and high risk, just with the thought that, that's about a 40-year horizon on some of these assets being affected by sea level rise.